Hello again, higher algebra students, back here with Unit 10, Lesson 4, which is graphing polynomials. And just right here on the first slide, you can already see kind of the idea that we're heading toward here when it comes to x-intercepts and end behavior and things like that. So you see, for instance, if we have a constant function with degree 0, so it's just, for instance, y equals 3, then we'd have a graph that looks like this. If we had y equals 3x, it might look like this. Y equals x squared minus 2 or something like that. But again, the key being that this is really x to the 0 on this one, x to the first, then x squared. If it's x to the third with something, then it might look like this. If it's x to the fourth, then it may look like this, x to the fifth. And if you just look at it, if you count the number of, so when it's x to the 0, it's just going to be a horizontal line like this all the time. When it's x to the 1, it'll be a diagonal line or horizontal, where it's diagonal up or diagonal down. It technically could be, if it was 0x to the first, I guess it could be a 0 slope. And then if it's second degree, you see it has 1 bend in it. If it's third degree, you see it has 2 bends in it. If it's fourth degree, it has 3 bends. So basically, degree minus 1 equals number of bends, if you will, in these graphs. Fifth degree had 1, 2, 3, 4 bends. Okay, so again, just a reminder of this table here as we're looking at kind of following our same general pattern. So if we have an odd degree and a positive leading term, then we're looking at something like this. And again, this is a little different order than the last time I showed this in class, but positive and even. So something like x squared. X squared would be a going up both directions. Odd and negative would be, again, odd means it's going in opposite directions. Negative means it would be backward from the other. So you can see these two are backward from each other. And then even degree but negative, so like a negative x squared would look like this, because a negative x squared with something else added onto it would look like that. X squared would look like that. Something like x to the third. So like here, if it was 1x to the third, that would look something like this. And again, if it was negative 1x to the third, then it would be the opposite. So it would look like that. And you can see those two are just flipped from each other, just like these two are flipped over from each other. So leading term of the polynomial here, we would have x and an x and we have leading coefficients then really of 1, 1, and 2. So 1 times 1 times 2 is 2. And then x times x times x is x cubed, because again, x times x times x is really x to the 1 plus 1 plus 1, which is x to the third. So we've got an odd degree. So we're in this column here. We've got a positive leading term. So we are right here. Let's get a different color. And so our end behavior here would be down to the left and up to the right. So again, this would be as x goes to negative infinity, y also goes to negative infinity. As x goes to infinity, y goes to infinity. So that would be our end behavior. Now, we also want to know how to find the x-intercepts. So again, if we utilize the idea of end behavior combined with x-intercepts and knowing our degree, we can start to do rough sketches of these. So for instance, using the zero product property to find our x-intercepts here, that would mean that if this equals 0, that means x minus 2 has to equal 0, or x plus 3 has to equal 0. Well, if you add 2 to both sides, that would mean x equals 2. And you subtract 3 from both sides, so x equals negative 3. So our x-intercepts here would be at negative 3, 0, and at 2, 0. So those, again, would be our x-intercepts, and we could figure out what our end behavior would look like. We see that this is x times x, so it's actually an x squared. And again, what that means then is that this graph, if we were to draw this in, since it's a 1x squared, that means its end behavior would be up here. So this graph would look something like that. And so we have this graph that looks like this with these x-intercepts. Again, that end behavior that's going up. The other thing is the y-intercept. And so the y-intercept, which is actually something we'll split up in class, we won't talk about it on the same day, but the y-intercept ends up being in this function. If we were to FOIL, it's x squared, outsides is plus 3x, insides is minus 2x, and last is minus 6. So this is really x squared plus x minus 6. Well, if you recall, when we originally talked about polynomials, and the second degree polynomials specifically, we talked about how the last term, the one without the x, is really the intercept. So the intercept here is negative 6. So this point right here would be 0, negative 6. So that would give us that y-intercept as well. So as we move down to the second one here, and we look at, first of all, zero product property. So that would mean x plus 1 has to equal 0, or x minus 2 has to equal 0, or x plus 5 has to equal 0. And from there, you subtract 1, so you've got x equals negative 1. You add 2, so you have x equals 2. Or you subtract 5, so you have x equals negative 5. So again, there's 3 zeros here because this is a third degree polynomial. Okay, so if we put in the zeros on this one, we've got a 0 at negative 5, 0. We've got a 0 at negative 1, 0. And we've got a 0 at 2, 0. We also know that our leading term is x cubed because it's x times x times x, which means this goes up to the right and down to the left as an odd degree, but with a positive coefficient. So it ends up going like this on the right side and going down here on the left side. So what really happens here is we somehow cross again, and then we finish going up like that. Again, we'd have to look a little deeper to figure out intercept and so forth, to figure out where exactly we're crossing on this y-axis, but we can do that pretty quickly because that's really just 1 times negative 2, which is negative 2. Negative 2 times 5 is negative 10. So again, just like up here, it was, negative 2 times 3, here it's positive 1 times negative 2 times 5, which is a negative 10. So you can see my drawing is a little off here because my intercept is supposed to actually be negative 10. So it probably looks something more like that, where my y-intercept then is at 0, negative 10. So as a lesson here, you want to, if you're going to draw this, get your y-intercept first before you draw it so that you can have a sense of where we have to cross that y-axis. So it's a little bit of a connect the dots at the end. We get all of our x-intercepts on the axis, we get our y-intercept on the axis, and we work from there. So just looking at this third one quickly, we've got x minus 7 equals 0, or 2x minus 3 equals 0, or x plus 9 equals 0. Those would be to find our x-intercepts if that whole function equaled 0. So we add the 7, and we've got x equals 7. Or we add the 3 to both sides, that's 2x equals 3 divided by 2, so x would be 3 over 2. Or we subtract the 9 from both sides, so x would be negative 9. So again, if I put these on here, if this is negative 9, 0, and this is 3 over 2, or 1/2, 1 and 1/2, 0, and then we've got 7, 0 at the end. Okay, so there's our x-intercepts. Well, now let's just get our y-intercept quickly. And our y-intercept is negative 7 times negative 3, which is 21. And then 21 times 9, and 21 times 9 here is 189. So what that's telling us here is that our y-intercept is actually way, not there, but way up above that. And so the other thing is our leading terms are x, 2x, and x. So if you multiply those leading terms together, that would give you 2x cubed. So again, that means we have an odd degree and a positive coefficient, so that's going to go up to the right and down to the left. You can see here what's going to happen is we really go up through here and way up there, and then come back down and then go there. And so what I've done is I've hit all of my x-intercepts again. My drawing is not to scale, so I didn't actually hit my y-intercept, which was way up at the top of the screen here at 0, 189. But then I went through, came back down, went through this x-intercept, went below the axis, then came back up through this x-intercept, and then my end behavior on the right, again, it's up to the right and down to the left, which I have right here. So you can see there's a combination of things here. X-intercepts by solving for the zeros, Y-intercept by multiplying the three numbers, which in this case were -7, -3, and 9, and then the leading behavior, or the end behavior, by looking at that leading term to get whether it's an even or odd degree and whether it's a positive or negative coefficient. So another example here, we're going to find these x-intercepts first. So we've got x plus 2 would have to equal 0. Again, we're trying to make that whole equation equal 0. So either x plus 2 would have to equal 0, x minus 1 would have to equal 0, or x plus 3 would have to equal 0. So we subtract 2 here, so we've got x equals -2. We add 1, so we've got x equals 1, or we subtract 3, so we've got x equals a -3. So again, our x-intercepts would be here at a -3, at a -2, and at a +1. So we'd have 1, 0, -2, 0, and -3, 0. Now we've got to find that leading term, which the leading term here would just be x times x times x, because again, we're going to multiply the term with the biggest exponent in each one of these sets of parentheses. And the biggest exponent here would be all these x to the 1s that we have. So x times x times x is x cubed. So again, that means we have a leading coefficient of 1 that is positive, and a degree that is odd here because of 3. So that means at the end of this graph, we're going to go up to the right and down to the left as our end behavior. And then let's just again add in that y-intercept point here. So the y-intercept is going to be number times number times number, because again, it's the last term of our standard form polynomial in this case, because it's the term without an x with it. So that would be a 2 times a -1 times a 3. So that's -2, -2 times 3 equals -6. So here's our y-intercept of 0, -6. So again, what we're doing here is you can see this y-intercept is between the right 2 points here. So that means we're going to be going kind of like this. And we don't know for sure where it necessarily hits this point, if that's at the bottom of that, what we call a relative minimum, or if it's at or local minimum, or if it actually goes below that point as it continues on. So what I mean by that is it could go like this, or it could go something like this. And to answer that question, we'd have to explore this graph a little further, which we aren't going to do right now. But again, you always have options like Desmos or your calculator to try and determine that, if that is the minimum at that point. So for right now, we're just worried about that end behavior and crossing all of our x-intercepts and that y-intercept. Another example here, same sort of idea. Our x-intercepts, as you can see here, we're now going to have 4 x-intercepts. So we've got these 4. So we've got x equals 5, we've got x equals -1, we've got x equals 2, and we've got x equals -2. And again, it's making the whole equation equal 0 here. So we've got the point 5, 0 as the first one. We've got the point -1, 0 as the second x-intercept. We've got 2, 0 as the third x-intercept, and we've got -2, 0 as the fourth x-intercept. Okay, so that means, again, we're going to cross this line 4 times, and the reason is because, again, the leading term is going to be x times x times x times x, switch colors here, x times x times x times x, which is x to the 4th, and again, that coefficient would be 1, so we have a positive leading coefficient and an even degree, and so that means our end behavior is going to look like this. Both sides are going up. Again, because that even coefficient, that means they have to go the same direction in terms of either both up or both down. And because the positive coefficient, that means it's both up. Now, the y-intercept here And this is where the scale of my graph is going to fall apart a little bit. But the y-intercept would be, again, -5 times 1 times -2 times 2. So -5 times 1 is -5, -5 times -2 is 10, and 10 times 2 is 20. So our y-intercept is 20, and so again, we have to hope that this seems to make sense with where our end behavior is and where our x-intercepts are. And so let's take a look here. So if we come down from up here, again, we don't know how low we go, but I'll just come right back up, and then I have to come right back down. Oh, nope, not right back down, sorry. So if I come down, come up, I gotta hit that that y-intercept right there, then come back down. All right, it worked. So again, I made sure that I had my end behavior going up in both directions. I hit all 4 of my intercepts on the x-axis, and I hit my y-intercept. And again, I didn't have to change anything. I have 3 bends in my graph here because of the being x to the 4th. There's my 3 bends in the graph. Again, number of bends is 1 less than the degree. So connecting the dots worked out okay here. Again, this isn't probably the exact graph, but it is just a sketch of what it may look like here. Number 6, this one's a little different now. It's going to take a little more work to get our intercepts here. -2x plus 3 equals 0. And then we've got x minus 1 equals 0 and x plus 3 equals 0. But this here, when we subtract the 3, we now have -2x equals a -3, so we divide by -2. So one of our x-intercepts here is a positive 3 over 2, since it's -3 over -2. So that's 1.5. Here's an x equals 1, and then an x equals -3. And again, it's all just about what makes each one of these terms equal 0. So if I put any of those x values into the first, second, or third term respectively, that would make that term equal 0. So we've got x equals 1 as one of our intercepts. We've got x equals 1.5, which is 3 over 2, as another intercept. And then we've got -3 as our third intercept here. Now in our leading term, as we look at this, our leading term is going to be -2x times x times x. And again, that's just, the biggest exponent in each one of these individual terms here. And so that gives us a -2x cubed. Okay, a -2x cubed, again, obviously that means we've got a negative leading coefficient and an odd degree. Okay, well, odd degree, the positive coefficient looks like this in some way. So the negative coefficient, again, odd means it has to go opposite directions. Okay, so this would be positive and odd here. So negative and odd, again, would mean opposite directions, but now this is flip-flopped, so we're going to go something like this. So we have to be up to the left and down to the right. Okay, so now we've got our x-intercepts, we've got our end behavior, which looks like this. And again, it's opposite directions because it's odd, and it's up on the left and down on the right because it's negative. So from here, what I'm going to do is I'm going to find that y-intercept. So that y-intercept here is 3 times a -1 times a 3. So 3 times -1 is -3. -3 times 3 is -9. Okay, so we get down here to 0, -9. That would be our y-intercept. So again, what we're hoping is, can we make this graph work with these x-intercepts, this y-intercept, and this end behavior, which we should be able to do, presuming we've done everything correctly. So what we see is we know we need to start from up here and go through this point. Before we can go through the next x-intercept, we have to hit the y-intercept because, again, that's between those two, right? An x value of 0 is between an x value of -3 and 1. So we got to hit the y-intercept there. We come up and hit the next intercept. We come back to hit that last x-intercept so that we can hit that down to the right. So again, we've connected the dots properly. We hit both end behaviors. We hit all three x-intercepts, and we did hit our y-intercept between the leftmost x-intercept and the middle x-intercept. So they were good to go there. Couple more here. So this one has four terms. So we have x plus 2 equals 0. We have negative 3x minus 1 equals 0. We'd have x plus 3 equals 0. And we'd have x minus 5 equals 0. So we'd have x equals negative 2, or we can add 1 here and get negative 3x equals 1. When we divide by negative 3, we've got x equals negative 1/3 as a, negative 1/3, because we had a positive 1 and divided by a negative 3. So that's negative 1/3. This is x equals negative 3 and x equals 5. So we've got the 4 zeros here to start with. So again, negative 3 is our most negative. Actually, probably the best practice to do here is to start with the x-intercept that's the furthest from 0. So you kind of set your scale that way. So 5 is the furthest down the line. It's our only positive one, but it's more about how far away from 0 it is. So if it were negative 6, that would be further away from 0. So we'd probably want to do that first. But doing 5 first allows us to kind of set what our scale is going to be roughly on what's called here a naked axis, or an axis without any numbers on it to start with. So then this would be our negative 3, 0. Right next to it, we'd have a negative 2, 0. And then right close into 0 there, or into our origin, we have negative 1/3, 0. So we've got 4 x-intercepts here, which makes sense because our leading term here is going to be x times negative 3x times x times x. So that gives us a negative 3x to the 4th, which of course is a negative coefficient and an even degree. And again, even degrees travel in the same direction. They're either both up or both down, but both up is when it's even and positive. So this is negative and even. So this is going to be both be down. So we know that we have to end here and end here some way. Let's figure out our y-intercept quickly. If we just look at this, first of all, our y-intercept, if this is going up here, it does look like we need to hit our y-intercept before we come back down, because our next value is a negative x-intercept right here. So hoping that our y-intercept is somewhere up in this area up here. So let's take a look. So we have here, change colors, a positive 2, a negative 1, a positive 3, and a negative 5. So again, we're just multiplying the values without x's, because that last term without an x, if we have it, will be that y-intercept. So we've got 2 times negative 1 is negative 2. Negative 2 times 3 is a negative 6. Negative 6 times a negative 5 would be a positive 30. So our y-intercept is way up here, and again, this still isn't to scale, but it's way up here at 0, 30. And again, 30 is just the product. If you multiply all these numbers, 2 times negative 1 times 3 times negative 5. So what we know then with this is that really this goes all the way up. Actually, it probably goes something more like this, where it maybe hits this on its way back down, so that I can get down to that point, which I kind of missed there still. And then something like that. Again, we don't really know at all how low or high these areas go. But we do know that in general, it has to cross these 4 intercepts, those 3 in this one. It had to hit that point 0, 30 up there, and it had to go down in both directions at the end. So, sorry, it's a ugly graph with all that writing on it, but the green one again is kind of our general format there. One last challenge example here, and this one, you can see it. We've got an x squared term up front now. So to find the zeros is going to be a little more work. So first of all, on the first term, what hopefully stands out is that we are subtracting a perfect square. So this is actually x plus 6, x minus 6, which again is the general routine. If you are subtracting a perfect square, then it's just x plus and x minus the square root of that perfect square. And again, the reason being, if we FOIL this, we've got x squared minus 6x plus 6x minus 36. So the x terms just take care of each other there, so it's just x squared minus 36. And then we also have to factor this equation. So we need two values that multiply to 6 but add to 5. Well, two values that multiply to 6 but add to 5 would be x plus 3 and x plus 2. So now we've got our zeros. So our zeros here would be negative 6, 6, negative 3, and negative 2. Again, any value that would make one of these terms be 0, that would make the whole equation end up equaling 0, which means these are our x-intercepts. So again, I'll place the 6's first. So this would be negative 6, 0. Right over here would be 6, 0. We've got a negative 3, 0, which would be about halfway to that negative 6 naturally. And then we've got a negative 2, 0. So we've got our x-intercepts. Okay. In terms of end behavior, well, this ends up being x times x times x times x to give us that leading term. And so x times x times x times x is x to the fourth. And of course, it's 1x to the fourth. So this would be positive and even. And positive and even, as terms of end behavior, goes up. So these are both going to go up on the ends. And then we just have the y-intercept. And the y-intercept here, you could do a couple different ways. We could just take negative 36 times 6 if we wanted to. Or if we go down here, we've got 6 times negative 6 times 3 times 2, which does the same thing for us here. Either way, you should get a y-intercept of negative 216, which is negative 36 times 6, or multiplying each one of these. So the y-intercept, again, obviously I'm not to scale here, but the y-intercept is way down here at negative 216. So if I were to continue this line on, there's our y-intercept, which again means from the right side here that when I come down, and I already made this not steep enough, when I come down, I got to get all the way down here, and then all the way, oh, that's not very pretty, all the way down here, and then all the way back up to hit that negative 2. Oh, sorry, I think I wrote 2 there. You maybe noticed that right from the beginning. Hit that negative 2, and then I come up to the positive and back down to the negative, and there we go. And again, these bends could be at much higher or lower points here. This one we know is correct because it's at the y-intercept. But the other two bends, we don't know necessarily how high or low they go. Put an arrow at this end here as well. And so again, we have 3 total bends because it's a 4th degree polynomial. We hit all 4 of our x-intercepts and we hit our y-intercept along with the correct end behavior. Thank you very much for listening. As always, if you have questions, please ask.